Hi, this is Lisa Knight. This is Lecture 10. We'll be learning about electric potential and electric potential energy in this lecture. Electric force is a conservative force, just like gravitational force. Therefore, there must be a potential energy associated with it. So remember that when we studied gravitation, we talked about the fact that masses are always attracted to each other. And the reason why a mass on Earth falls to Earth is because there's this gravitational field around the Earth that is due to the fact that this mass is attracted and being pulled down by the Earth, by the force, the gravitational force that we call weight. And the closer it gets to Earth, the harder and faster it accelerates, right? So and actually I should clarify, the faster it moves, it gains speed by 9.8 meters per second every second as it falls. So as it falls, if we let go of it at point B, as it falls, it would gain speed and thus gain kinetic energy. But at the same time, it has to get that kinetic energy somewhere, and it comes from the stored potential energy it had at point B. So it will always fall in the direction of decreasing electric potential energy. If we try to move it up, we have to do work to lift it up against gravity. And if the higher it is in the field, the more gravitational potential energy it has. Electric charges work the same way. Remember that an electric field points from the positive side of the field to the negative side of the field, and that Q naught is considered to be a positive test charge. If we hold the positive test charge at point B, it would be kind of hard to do because its natural tendency is to move in the direction of the field lines. And it will get faster in the direction of the field lines, which means that it too gains kinetic energy and must be losing potential energy as it goes and moves and accelerates in the direction of the field. If we try to move it from B to A, we have to do work moving it to give it, and thus gives it more potential energy. And then if we let go at point A, then it would fall, and decrease its amount of electric potential energy, and at the same time have an exact equal amount of increase in kinetic energy. Nonetheless, either the field is doing the work or we're doing the work, and the amount of work is equal to the opposite polarity, gain or loss in the electric potential energy. So work is equal to force times distance, and consider that falling charge. The force that's causing it to the charge to fall, is the electrostatic force, which can be calculated by the charge times E, the field strength. And that force times the distance gives us the work done moving it. And remember that in this case, it's losing energy. So the work done on it will be a negative value. And the gain of potential energy is equal and opposite to the work done moving it. So the formula for finding the work is negative Q naught ED. It will be measured in joules or Newton meters. And the formula for electric potential energy is the same formula, but in the opposite direction, positive Q naught ED. So a proton is going to be moved from point A to point B in the field. How much work is done, and what is its change in potential energy? So that work would be negative 1.6 e to the negative 19 coulombs times 200 newtons per coulomb times, I'm just making up a distance of 1 meter, because it's not specified here. And that would mean that negative 3.2 e to the negative 17 Newton meters or joules of work were done. And its change in potential energy was positive 3.2 e to the negative 17 joules. Sometimes it's more useful to think about how much energy each coulomb will gain or lose. So we have to introduce a new term, the electric potential. This is not the electric potential energy, which is measured in joules. This is how many joules per coulomb is lost as any charge moves to and from point A or B in the field. The electric potential is given by the symbol V because it's measured in volts. Its formula is the change in potential energy over Q naught, or negative work over Q naught, which means its units are joules per coulomb, which we will call a volt. It is important to note that an electron volt is not the same thing as a volt. If you rearrange that equation for delta U, you get delta U equals Q naught times delta V. So an electron volt is, by definition, the energy to move one electron 1 volt through the field. Going back to our original problem, what if we wanted to find the potential difference between points A and B? The potential difference is delta U all over Q. Delta U was 3.2 e to the negative 12 joules, and the charge was 1.6 e to the negative 19 coulombs. So our voltage is 200 volts, or 200 joules per coulomb. The electric field and voltage are also related to each